Steve places a zinc nail in a. Welcome to this class doing a past paper. Let us pray. Holy and righteous God, as we come to you in holy prayer, please strengthen us, bless us, protect us, help us, we pray. In Jesus' name, amen. Steve places a zinc nail in a beaker. Where would they? Containing right report in a man. You can take some notes as you go along. Steve play are the answers, because obviously you know them there. You know what the questions are. So this is paper 2007. Question 2, page 66 in the CXC past paper booklet. Yeah. No, let me say another thing. The guy do the titration for the front. Steve placed a zinc nail in a beaker containing aqueous copper 2 sulfate. Figures 2A and 2B indicate what happens to the contents of the beaker over a 3-day period. No. Based on the observation, the observed differences. Well, before we even do that, we have a zinc nail also. And what is the zinc nail placed in? Copper 2 sulfate, yes? Which would be blue, right? Now, then tell the color, deep blue solution, good. Now, after some time, it turned to a pale blue solution and warm to the zinc nail. It shrink in size. Are we seeing that? And a shiny red/brown solid is produced. And a pale blue solution is formed. So you have to say it is really blue, deep blue. Like very blue. And then the blue color fade to a pale blue. Alright. Based on the observed differences between figure 2A, this is the point that you say, right? Based on the observed differences between figure 2A and 2B, name 2 ions that would most likely be present in the beaker after 3 days. Zinc 2 plus, good, because you know, say that about becoming from the zinc metal, right? What else? They say ions, they never say solid. Copper is not ion. Ion of copper. Copper is a metal. Why would it have a negative charge? Which ions copper produce? Which ions does copper produce? Which two? Yeah, copper 2 plus. About then say 3. A 3. Oh, 2. Alright, we're good. So that's it. Okay. And if they say that this thing is a copper sulfate, obviously SO4 2 minus would have been there also. Are we clear? SO4 2 minus. Are we clear? Yeah, that should be it. Those 3 would have been it. And obviously, probably some degree of, although this is a higher level chemistry, both hydroxide from water also, or the hydronium ion from water. But keeping it simple, these, because those are straightforward, right? Now, you know what? Let me use my marking tool or a writing tool for us. Copper 2 plus and zinc 2 plus. Now, it's write ionic equation to show the reaction that takes place in the beaker in figure 2b. Explain why these reactions occur. What happened in figure 2b? So? Are you catching that, young lady? Zinc takes the place of copper. What kind of reaction that? Good. Single displacement reaction too. So, I'm going to show you the reaction that would have occurred, right? And then we figure out the ions, the net ionic equation from that. Okay? So, what are we? Look what this thing is. What do? Look what the board. So, we put zinc metal, right? What allowed this reaction to happen? Zinc solid in copper sulfate aqueous to produce the red brown metal we see obviously was solid copper. And obviously, if zinc take the place of copper and a zinc 2 plus, just like our copper 2 plus, we'd have gotten back zinc, we'd have gotten zinc sulfate, and that's an aqueous salt. Are you clear? No, why did this occur? Hmm? Which is the explanation. Why? This is not the ion equation yet. Just are showing you the balance chemical equation, showing that we have one metal displacing another metal from its salt. Why this? Why does this happen? Good. Zinc is higher in the reactivity series than copper. Are we good? Good. And so, what is the ion equation you get from this? Balance chemical, the balance, yeah, man, the balance. Good. One zinc, one copper, sulfate, sulfate. Good. Hmm? Alright, so we could ionize it. You can do this on the back of the paper or some if they do if you have no space you can do it on the back of the paper, okay? So zinc solid plus copper, so we show them how we arrive at it. Plus copper. We will work it out and show them how we arrive at it. Just want to write this, alright? That's aqueous because it dissolves in water, obviously. Copper sulfate does that, producing zinc sulfate and solid, and that's aqueous plus solid copper. Now, can we ionize this solid zinc right here? So we put it back. Can we ionize this aqueous copper sulfate here? Good. So it's pretty. Why I was splitting that? Copper 2 plus aqueous plus SO4 2 minus aqueous goes to form. Can we ionize zinc sulfate here? Is it aqueous? Good. So we end up with zinc 2 plus aqueous plus SO4 2 minus aqueous. Can we ionize solid copper here? Eh? Good. No, we can't do it. Solid copper. So wait. What is spectator ion name as then? Good. I see him on both sides. And so my or my ionic equation, zinc solid plus copper 2 plus aqueous also form zinc 2 plus aqueous plus solid copper. Are we good with that? That is how we make ionic equation. Now we just write that down in there. So zinc solid plus copper 2 plus aqueous also form zinc 2 plus copper solid. So what are we finding out here? We are seeing here that one of these metals got oxidized and one of them got reduced. Which one of the metal then? Barry, pay attention. Which one of those metals got oxidized, which one get reduced? Zinc got oxidized and excellent. See there? Zinc was in solid state and a zero oxidation state. What over here, we have a +2 oxidation state. Why? Because he would have given up electrons. Oxidation state rises when you get oxidized. Am I clear? You give up electron. Who give up electron to? Two electron. Who give to? Copper. And copper got electrons. He went back to a zero oxidation state, having lost no electrons now. And if oxidation state drop, say you get reduced. Good. Going to when we pull the redox out there, name a type of chemical reaction occurring in the experiment. Good. Single displacement. Because only one thing I get displaced. You understand? Single displacement. Some people would say a redox reaction might be, it definitely is a redox reaction also. So if you say that might be I get it right, but this is the more preferred answer. Okay, this is more preferred answer from the perspective that it is a metal question. Now, comment how the rate of reaction might be affected if zinc nail is replaced by each of the following. If we take out the zinc, if we use some magnesium metal instead, how would the reaction rate be? There are 5 factors that affect the rate of a chemical reaction. Okay, what are these factors? And if you know them, concentration, eh? Catalyst for a gaseous reactant, the pressure, with the funny, more pressure. So the more the concentration, the faster the reaction rate. The more the catalyst, the or the use of a catalyst, the presence of a catalyst make the reaction rate faster, make the reaction occur faster and produce more product in a less time. If you put more pressure, if you use like two gases, yeah, like you react H2 gas and O2 gas, they are going to react faster if you pressurize them. Temperature, the more temperature you put, like you heat up the thing faster, heat up the thing more, the reaction rate increases. Are we clear on that? So those are four major factors that affect the rate of a chemical reaction. Oh yes, and the fifth one is particle size. If you increase the surface area, like if you grind out the particle like if this was a big old brick, yeah, and I want reactant, if I want this to react faster with something else, we powderize this. You understand? So each individual particle can react more quicker because they can now take up energy easier and collide better. Are we clear? No, the people must say, and that's all about reaction rate. Now, if you use magnesium metal instead of the zinc, what that would the reaction be faster? Would the reaction be slower? Why? Excellent. So, because magnesium is higher in the reactivity series than zinc, please stop calling me magnesium a careless zebra. Zinc is 2 places down, right? So, magnesium, the reaction rate would be faster. The reaction would be faster. Would I see anything? I would see more production of copper in less time. Explanation: magnesium is more reactive than zinc. Are we good? What about lead? Would the reaction be faster? Would the reaction be slower? Hmm? Good, slower. Why? Lead is lower than zinc. Good. So the reaction would be slower. Would be slower as more, not as more, would be slower and less copper would be produced or would be discharged in less time, in more time also, and less copper would be discharged in a given time period. Let's put it like that. A given time period. Explanation: lead is less reactive, is are lower in the reactivity series than zinc. And you get a little 6 mark easy like peasy. Less than zinc. Are you clear? Now, electrolysis question. Steve modifies the apparatus in experiment as shown in figure 3 below. State what effect this experimental arrangement will have on the bulb. So the hombre have the aqueous copper sulfate as a electrolyte. Are you seeing that? Him have the zinc there and him have a graphite rod here. What would happen to the bulb? when this circuit is made, this electrolytic cell is made, what would happen to the bulb? Hmm? The bulb would have turn on because electrons are moved from, uh, cations are go to, anions are go to the anode here. No, so this is the positive. The big one mean positive, the little one mean negative. Are you clear? Good. So make sure say this is the anode and this is the cathode. No, anions are go to zinc, to this zinc electrode, lose electrons and basically flow around the circuit. Are you clear? Are we good? Or you can appreciate it like, yes, matter of fact, that exactly. No, bulb would light up. Bulb would light up. Anyway, take it from bulb will light up. Did they ask for explanation? Explain your answer. Anions are electrons really. Anions lose electrons at anode, which flow around the circuit to cathode. Flow around the circuit to cathode. And be really and truly, a flow of electrons is defined as what? A flow of electrons, what is a flow of electrons defined as? Eh? Electricity. If electricity therefore go through the bulb, will it light up? Eh? Good. Electric, electric, electricity slash electric current, which will light up bulb, which will light up the bulb. Are we clear on that? No. Can I scroll down? So that's now my electrolysis setup. It produces electricity. Okay? It can produce electricity. These are the first type of batteries. Electrolysis enable mankind to actually create battery. Yeah. That's where that come from. Yeah, 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 investigator. Hmm? Aye. Learn which will light up the bulb or cause the bulb to light up. Now, next question. Lowry conducts an experiment to investigate how the mass of a catalyst, magnesium 4 oxide, which we know is an excellent catalyst that is used for the decomposition of hydrogen peroxide, H2O2. So, manganese 4 oxide, MnO, is an excellent catalyst. We break down hydrogen peroxide and make him, well, it allows the decomposition, the chemical breakdown of hydrogen peroxide to occur faster. Are we clear? Good. So Lowry conducts an experiment to investigate how the mass of a catalyst, manganese 4 oxide, affects the rate of production of oxygen during the decomposition of hydrogen peroxide to form water and oxygen gas. Are you clear? And that H2O2 breaks down or decomposes to produce H2O and oxygen gas when you put manganese 4 oxide in it. Okay? Manganese 4 oxide did not take part in the chemical reaction. A catalyst does not take part in the chemical reaction. It only allows the reaction to proceed at a pathway that is more energy efficient. And so it uses and allow the reaction to need a lower amount of activation energy, the energy required to make a reaction occur. You make the catalyst drop that energy, that activation energy, and make the reaction occur with less activation energy. So yeah, faster. No, yeah. Mm-mm. You can look on those as boiling chips. The same function where boiling chips have in a chemistry, I see him that would have. Now, what is boiling chips used for? Boiling chips are used to make, to lower the boiling point. I mean, the boiling point of the substance, of the liquid, boil faster. How does that happen? You see, because you're putting the solid substance, so someone's asking a question, guys. Not it doesn't pertain directly to the price paper. Me answer it. It's a good question. So when you put a solid substance within a liquid and you try to boil a liquid, what do you think the liquid are going to do? No bounce funny, bounce all over it, right? Because you have a solid in it. What do you think the bombardments will be? Greater or lesser? Good, because you have more foreign particles in there. So what we say, a foreign particle in a liquid, using water as an example, lowers the boiling point of water because the water molecule are bombard faster. Or bombard for more things, they are bombard all over the place, and when they book up on a solid, they bombard against that. And so the entire bombardments are even more now. And so that leads to what you think, increase in kinetic energy or a decrease in kinetic energy. The kinetic energy is energy due to movement of particles. So will it be higher now or lesser? Higher. And if the kinetic energy higher, that means more heat energy is also present. And if you have more heat energy, that means that the reaction will occur faster. But that one is not really a chemical reaction. A boil by something. You no reaction happening. So that is just a conversion of state of matter from liquid to gas. So the boiling point is lowered because of the bombardment, and so you have a less boiling. You have a less boiling point. And so the water boil faster. So boiling chips and the needle and all of them is sitting there is used on that premise. So for lower boiling point. So name three other factors other than a catalyst which can affect the rate of a chemical reaction. So glad we named them out before. Eh? Repeat. Temperature, particle size. No, brother, I'm never said density. Particle size, check your book. You need to write them down. Yes, five of them. Pressure of a gas, right? Give me something else. I mean, I use no gas. Concentration. Concentration. If you're not using a gaseous particles, you have to mention pressure. The pressure only affects any of the big gases. This hydrogen peroxide eventually, initially was a liquid. It's the same one your mother put on your coat. You know hydrogen peroxide? White liquid they then put on coat. And it's in an odor. You don't know it? But no wow. Mm. Write a balance equation to show the decomposition of hydrogen peroxide by manganese peroxide MnO2. So this is the balance chemical equation. I would have gave it to you in Redux. I really hope you guys watch, especially that last Redux video. So anyway, H2O2 decomposes in the presence of the catalyst. The catalyst always got the top MnO2, just like how the temperature would have go below you. You understand? And the pressure. So MnO2 to produce water, H2O plus O2, and it's a liquid, O2, gas. Yeah, that's that. Eh? No. This is when the hydrogen peroxide is occurring as a reducing agent. You see, if you mark her as an oxidizing agent, he would have produced water and hydrogen gas instead. So there are two type of decomposition reactions for hydrogen peroxide if it's being used. Because remember now, he is both an oxidizing agent and a reducing agent. But because the manganese peroxide is reducing him, it help him now to give him reduction reaction. Not his reaction that occurs or decomposition reaction that occurs when he acts as an oxidizing agent. So or a reducing agent. So basically the substance that brings about reduction, right? So water plus O2 and that thing do when he behave as a reducing agent. One time I'm gonna make an O2 gas. Okay? All right. Let me make sure that it's balanced. Um, Two, 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 two. We put two here, so much we get. Four. Yeah, four, four. Us. Hmm? Good. Yeah. Excellent. No, that's it. No balance, right? All right. So on page 11, figure 4 on page where? Our page 11. The page number them at the top. Can't decide the one for you. That me I say. So figure 4 on page with that there. Oh, down here. The graph. So figure 4 on page 11 shows the rate of decomposition of hydrogen peroxide as a plot of as a plot of grams of oxygen liberated per second against mass of catalyst for both a zero point 0.4 and a zero point 0.8 mole dm cube hydrogen peroxide is used. So them have two different concentration of hydrogen peroxide decomposing. Them have a zero point 0.4 and a zero point 0.8 mole dm cube concentration. Are we clear? When you see mole dm cube, that's concentration. Are we clear there? So you can get where them come from already, right? You really study how concentration will affect the rate of reaction. So explain why the plots in figure 4 are different. The figure 4 explain why the plots. So we have one plot at bottom, see there, with the zero point 0.4 mole dm cube, and tell you which one that be. And then you have a plot that is more steeper, and it deals with and it has a zero point 0.8. This is one with the zero point 0.8 mole dm cube concentration. Why is this one more steeper than this one? Which one of you were at class? And how does that affect reaction rate? Mm. If you have more concentration, you have more individual atoms in solution, and so there is more possibility for them hit up. So because zero point 0.8 have more dm cube, have more atoms of hydrogen peroxide, plug in this in me, than than a zero point 0.4 mole dm cube solution, you're gonna have greater bombardment in the zero point 0.8 mole dm cube. Am I making sense? If you have a 15 orange in one bag, the orange them you have more orange and lick up together like 15 bag of orange. And if you now you have a bag of orange with 5 orange in it, also the zero point 0.4 is like an orange bag with a small amount of orange in it. Them not go bombard as much as if you have a bag with 15 orange in there. Am I clear? So zero point 0.8 have more atoms in it, more molecules of hydrogen peroxide than the zero point 0.4. Am I making sense here? And so they will bombard more, and so the reaction rate will be more. Are we clear? So the graph is actually saying that. Watch me. I'm going to study something. The graph is actually saying, all right, yeah, at any given time, watch this. At any given time, at any given time, the one that has the greater concentration will produce more moles of oxygen. Look on the board, no man. Turn on, 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 turn on. At any given time, the one with the greater concentration, the graph plotted with the plots of the greater concentration one, shows that the one of 0.8 mole m cube concentration produce more mass oxygen at any given time than the one with the lower. Let's look at one. Let's look on the mass of the catalyst. If you use one gram of manganese oxide, the one with the lesser concentration produces 0.0005. The rate is 0.005. Are we clear? So that the reaction no occur as it only produces Let me read it next way. Yeah, let me just use the time. 0.005, right? Right there. That comes there, right? This one that comes there. We use the same time frame, the same rate, right? So we cross. All right. So the one with the greatest produces a 0.5 gram at that rate, and the one with the 0.4 produces a 1 gram. When you use the mass of the catalyst, you get where I come from? Really? We say we can get a stronger grasp on a graph. The mass of the catalyst is there. In both cases, if I use 1 gram, read for X. If I use 1 gram of catalyst for each case, film reaction rate is lower. This makes sense now. Than if I use, yeah. And when I use a 1 gram catalyst, 1 gram of the catalyst, manganese oxide, with the one of higher concentration, his reaction rate is faster. It's about what 0.125, right? So, are we seeing that, guys? Are we interpreting that? So, you have the mass of the catalyst. You have 1 gram of manganese oxide. You put him in the one. You put him in the hydrogen peroxide of lower concentration. Him reaction rate lower for that. Carry it across. Lower. You take the same 1 gram, and you have 2 beakers set up, and you put it in the one with the higher concentration. What his reaction rate is what? Lower or faster? Faster. And it is the same behavior. Me increase the mass, the reaction rate increases, no so, as I would have expected. Yeah, for that the one. But for the lower one, film reaction rate increases, morning increases also, but much more than the one with the lower concentration. Are you clear? So it makes perfect sense. So them are look on two things in the one graph. Yes?